So, hi, I'm Pete Harris again. Sorry. And this talk's going to look at Vulkan best practices for mobile development. Some of this is Vulkan, some of this is just general mobile development and like what makes mobile different. I guess quick show of hands for anyone that was at Vulkanised 23. I know some of you were, but not many. That's good. If you were, some of these slides might look familiar. Physics is still physics, and it hasn't changed that much in 2 years. But if you haven't, welcome. So we are going to talk very, very quickly about mobile systems, what makes them different to console and PC. We're going to talk about tile-based GPUs, because most, but not all, mobile GPUs are tile-based, and why things like render passes are important. How does that translate into Vulkan best practices? So concepts more than API details. And then to wrap up a couple of highlights of kind of the new stuff that's happened since my last talk in 23 around kind of major new ARM functionality and how that manifests in terms of API usage. So let's start by looking at what makes a mobile system a mobile system. We're making small, light, battery-powered devices. The motherboard for a mobile phone is about the same size as a stick of chewing gum, and it's got stuff on both sides. It's super, super condensed electronics, and it's battery-powered. There's no big fan. There's no big heatsink. There's no fan. So needs to be energy efficient for battery life. Needs to be energy efficient for thermals. And that's really the overriding characteristic that makes mobile different to other platforms. To get the density and the energy efficiency, we tend to have sort of system on package and package on package manufacturing. So you've got your main logic die that has all the processing bits, CPU, GPU, modem on the base. We stack the DRAM die on top. And then you have a heat spreader that just is there. It's a very, very thin bit of metal. It isn't a massive, great PC heatsink. Trying to get heat away from that chip so that we don't melt the phone. And the biggest challenge for mobile is that for every watt you put in to drive the electronics, you get a watt of waste heat that you have to get out of that device. This means for mobile, the thermal budget that you can sustain without the phone overheating and starting to throttle is somewhere between 3 and 6 watts. That's going to depend on phone manufacturing in terms of physical design. It's going to depend on environmental conditions. Is the user in air conditioning or outside in a hot country? But the limits there are fairly tough. Physics is a tough taskmaster. The numbers can be higher than 6 watts, but the user is holding the device, right? If you've ever worked on power electronics and you've got a power supply with a 10-watt ballast resistor on it, try and touch it. Don't, please. They get really quite warm. So there are mobile devices where the device can get more than 6 watts away from the chip. We do see devices that are thermally stable at 8 watts. Let's just say you get sweaty hands, okay? Using your user as heat pipe water cooling is not cool. Where does the energy go, right? If we're talking about optimizing for mobile in the high end, this is very much about optimizing for energy. This is the power curve we get from silicon process over the last 10 to 12 years. It's a PowerPoint graph. It's not real data, but the trend's accurate. So going from silicon process in 2013 to where we are today, you get ballpark order of magnitude improvement for a reference circuit on silicon process alone, 10 times more logic performance for so many joules of energy. On top of that, we've been building better GPUs every year by a similar kind of curve. So maybe you get 2 orders of magnitude in terms of logic efficiency, which is kind of cool. Memory, not so good. It does improve, but the rate of DRAM efficiency in terms of DRAM generations is much, much, much slower. In fact, it's so slow that since I gave this talk in 2013, we haven't actually changed mobile memory technology at all. It was LPDDR5X in 2023, sorry. It's still LPDDR5X. So just compound interest over 10, 12 years, the gap between logic and DRAM is widening. When we talk about optimizing for mobile efficiency, especially for a data plane workload like graphics, that's increasingly turning into optimizing for bandwidth, 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 right? Logic is cheap. It continues to get cheaper. It's not free, but over time, bandwidth is becoming more and more significant as a percentage of the power. Mobile often gets compared against console, right? And it's a very simplistic comparison, and I want to chuck some data out there. So, this generation of mobiles equivalent to last generation of console. Yes and no, right? So without going into specifics of which console, but just like baseline relative numbers. So console gen 2 generations ago, console gen N-1, and the latest Mali Immortalis G925 12 shader cores running at a gigahertz. And that's thermally stable at 6 watts. We have 3 teraflops of FP32 FMA performance in a mobile power budget, which just blows me away, having worked on mobile graphics for a very long time. And this is FP32. Mobile GPUs tend to be very heavily optimized for FP16, Int16, so you can double that number if you can get away with medium P, relaxed precision types. So 6 teraflops of FMA performance in the shader cores. That's a supercomputer. It really is, right? And we can do that on a battery thermally sustainably. If we look at the same chart for memory bandwidth, if you go back 2 generations, you're somewhere around about 40 gigabytes per second of memory, ignoring the console memory system, what's bandwidth, which memory, and so on. It's not totally homogeneous. Console Gen N-1, you see the same kind of logic getting a lot better, faster than DRAM does. They've got the same physics constraints that we do a lot of the time. If you look at the latest high-end mobile phones, your thermally sustainable power is around about 30 gigabytes per second. Right? That's less than we got in console 2 generations ago. So we have lots of arithmetic performance. The challenge is, how do you get data into the GPU within 6 watts? The good news is the peak performance is a little bit higher. You can get it, like specific render passes maybe can go up to 70 gigabytes per second, but you can't use that over your whole frame. Your average bandwidth has to be down around about 30, otherwise you blow your power budget, but you get some good burst performance for short periods when you need it. So very much optimizing for mobile is about optimizing for bandwidth, both in terms of thermals, but also just in terms of the available performance ratios that you have. You've got lots of maths. The challenge is getting the bandwidth down so you can keep that math busy. So that leads nicely onto tile-based GPUs. Like, where did they come from? Why do we have tile-based GPUs in mobile? And the archetypal tile-based GPU, if you go back some time, is, I guess the goal is that you can keep your fragment bandwidth on chip during fragment shading. So we have a fragment shader core. Inside that, there's a tile RAM, and your working set for color, depth, stencil, and all your attachments, multi-sample, and so on, stays inside that tile RAM. We only load what we need from memory. We only store back what we need to memory. There's no spilling because of read, modify, write, because it's held inside the GPU. However, to make this work, we need to know which triangles contribute to which tiles. Therefore, you have to do your geometry stuff up front. And if you do that first, you've got to put that data somewhere. You can't buffer it in the GPU, it's too big. So we write that back to memory. So tile-based rendering is just a different design space trade-off compared to immediate mode rendering. We get efficient fragment shading, we get less efficient triangles. And that works brilliantly on mobile most of the time. We've got lots of UI use cases, lots of casual gaming use cases, compositing your browser. We want 2D to be as efficient as it can possibly be because phones do that all the time and battery life matters. The biggest impact this has at the API level is on scheduling. So with an immediate mode renderer where you're just pipelining draw calls inside the GPU, within a single draw call, you could have vertex shading and fragment shading happening at the same time. As soon as you complete a triangle, it can go into fragment shading. Because we have this split pipeline where geometry happens first, so we can build that tiling information, we then have to go and do fragment processing. We have a much coarser schedule. We can still get overlap, but you're having to overlap whole render passes, compute and render passes to get the different pipeline stages working in parallel. And this is where, for Vulkan, things like explicit pipeline barriers put some responsibility onto the application. You need to let us do this, otherwise you're going to start losing performance. So what does this mean in terms of API best practice? Yeah, render passes, right? So as discussed earlier, render passes are really there for tilers. They define the lifetime of that tile memory. What do you do at the beginning of a tile? What do you do at the end of the tile? That's your Vulkan load up and your Vulkan store up. And what happens during render pass stays inside tile memory. So render passes haven't gone away with dynamic rendering. We've just given you a much better abstraction for accessing the functionality without overcomplicating the software story. But render passes are still very much there, and they are still very much important. So don't load up load what you don't need to load. Don't store up store what you don't need to store. And please, please, please don't store up store multi-sample data back to memory. We have resolve attachments. That would happen for free as part of tile writeback. The multi-sample data never hits DRAM. The second part of being efficient for tile-based GPUs is don't create render passes when you don't need to. So Vulkan's an explicit API. If you tell us to create 2 render passes, you're going to get 2 render passes. And so your data is going to get round trip via memory. So if you have a 3D pass and then you're just compositing a UI over the top, you might write that back to memory, then read it one-to-one. This is a horrible use of a tiler. You're just round-tripping data for no good point, and bandwidth is evil. Right, so don't do that. Have a single render pass and just continue the data through. If you need to do things like kind of programmable blending, those kind of things, the new dynamic rendering, tile local read extensions are your friend. That's what they're there for. You can fetch the data straight out of tile memory, do your computation. You don't have to go through DRAM. So that's kind of basics. We often see this crop up where you've got a game engine with 2 subsystems that want to deal with render passes rather than something higher level. This is a really good use of things like secondary command buffers. Have each thing record a secondary, merge them into a primary later. That can be inside a single render pass. For pipeline barriers, so if tilers are very sensitive to conservative barriers. So if you have source stage is bottom of pipe, test stage is top of pipe, at the render pass level, you're going to serialize the world, right? Everything is going to run in isolation, no overlap. Your GPU PPA team will be sad. But we spend a lot of time trying to get apps to fix barriers. So if you've got a fragment to fragment dependency, set your test stage to fragment, your vertex stuff can run early. You still sequence the fragment shading in the right order. These are identical slides to slides I presented 3 years ago. We still see problems, but whenever we've presented this in the past, it gets presented in the context of render passes. But that's not the only problem. So I thought it'd be interesting for this talk to go and look at a bit more detail and what actually happens under the hood. So we have a bunch of Vulkan pipeline stages. There's many of them. From our point of view, we kind of group them together into a collection for different workload types. The only thing that's new is like, what's this advanced geometry thing? That's not a Vulkan term, that's a Mali term. What it means is that's where we put all the geometry stuff we don't like. Geometry shading, tessellation, transform feedback, all of those will have to write things back to memory, and then horrible things for a tiler happen. So try and avoid using advanced geometry features. When you record a command buffer, we map the workloads to a number of internal hardware streams. So view these as like the native command buffers that the driver is building. They're typed. And then we schedule those onto shader core endpoints when we actually want to go and run the work. And our shader cores have 2, a compute endpoint and a fragment endpoint. So compute goes into the compute stream and goes to the compute endpoint. Ray tracing pipeline goes to the compute stream and goes to the compute endpoint. Transfer goes to the compute stream, but it can actually end up in either place. Transfer is really ambiguous about where it runs, especially if you're patching frame buffers images. Our frame buffer compression unit only exists in fragment shading. I think Sergio mentioned that earlier. So that's a little bit of a pain point. Transfer is a little bit fuzzy. AG is just compute, so that goes into the compute endpoint. Vertex is just compute with some parallel binning in fixed function hardware. And then fragment shading goes to the fragment endpoint. When we talk about applications being efficient, within each endpoint, work runs serially. So what we really mean is keep one of the endpoints busy. Your critical path endpoint should be busy all the time. Then you've achieved your good parallelization and you're getting things running in parallel. If you're oscillating between them because of barriers, then you're leaving performance on the table. So we don't care so much that, say, compute's running all the time or vertex is running all the time. But if the combination of those types is running all the time, you've done the best job you can do. Then it's just a question of making the workloads faster. Some gotchas here. So the shared stream can cause false dependencies. So we have quite simple binary syncs currently in those queues. this gets fixed a bit later, which I'll talk about. But like if you had a compute barrier, if there was transfer in that stream, the transfer can block the compute barrier. Right? So that can cause some issues. Transfer being in two places can cause some ambiguities. When you have a transfer barrier, which type of transfer are you actually waiting for? The API has no way to express that. And that can cost some performance. So as an example of that one, you have a single Vulkan queue, you're dispatching a frame. We start the frame with a buffer transfer, copying some index data into a vertex buffer, into a attribute buffer, for example. We have two render passes that pipeline quite well, and then there's an image transfer at the end to blip to the swap chain. Now, this is not a good mobile example. We have unified memory. Ideally, you can just write straight into the write buffer without a transfer. You don't need to use transfers on mobile. And ideally, you'd render straight into the swap chain, and you shouldn't have an image transfer. So this is not good practice, but a good example. Next frame starts. We have a buffer transfer. Vertex shader wants to run. What does it need to do? Insert a transfer barrier, right? It needs the result of the F1 job before it can start the vertex work. But the transfer for F0 on the image transfer is still running. We can't disambiguate the stages. So that's going to get delayed. And then the fragment work will kick off a bit later. So because of that sort of false cross-frame dependency on the transfer stage, we end up deferring the vertex work later than we could otherwise run it. The recommended fix for this, for Vulkan, is to have alternating queues. So each queue has its own sync scope. So if we put a transfer barrier in the green queue, it doesn't have to wait for any of the transfers in the blue queue. So you just alternate two queues frame to frame, and you can avoid that issue. Yeah. A slightly different one is how many queue submits should you have per frame? We see a lot of like new developers over-optimize. Submits are bad, so I'm going to have one for everything. And this can cause different problems. So obviously, you're not submitting until the end of your frame recording, so nothing can start on the hardware. And then the next frame kicks off and everything runs. There is some idle time here, but let's imagine this is hitting its vsync deadline. So it's hitting 60 FPS. Are we all happy? Maybe, maybe not. The problem for this is frame latency. So from the time you start recording something, so your app has got its user input, started updating its animations, to the time you actually get something on screen, you've got the throughput you want, but you may have an extra swap chain in your rotation because you can't get things onto the display scan out fast enough. So this may be costing you a frame of latency, depending on what your workload is. If you submit as you go through, we can start the vertex work earlier, we can pull the fragment work earlier, the frame latency comes down, and things then pipeline a bit more nicely. The throughput is the same, right? The GPU workload's the same, you're still hitting 60 FPS, but hopefully you're getting your user doing something to the display updates a little bit faster. It may not help, you're racing your display deadlines a bit in terms of when it lands, but it can't hurt. So we've done a lot of GPUing in the last couple of years. I kind of wanted to call out some of the Vulkan API support we've gained in the devices. This isn't everything, right? This is very much Pete cherry picking a very sparse set from a whole load of work the GPU team's been doing. Mostly based on the kind of feedback we get from developers about where some of the pain points are. So we've heard from many talks in the last couple of days around debugging being a pain and sort of the device fault address device fault report and device address binding extensions. These are designed to help you debug device loss type issues if there's an issue, where's my crash? So we have both of these shipping now on new GPUs with new drivers. So you will get something out of device fault reports. It's not necessarily the most useful data, but it's what we currently have from the hardware. So this is going to be a work in progress for a while. We need some IP changes on the hardware side to give us better data on page fault and that kind of thing. But you see what we see. Is it perfect? No. It's often a breadcrumb we can pull on to help you debug things remotely, but work in progress. Some things on some of the presentations yesterday mentioned we have quite small buffer limits. Generally for Mali, that's either now 2 gig or 4 gig for all buffer sizes. Depending how much space we had in the descriptors on the hardware, we could fit things in. We've also significantly increased the maximum descriptor count limits for bind lists where you want to have a lot of concurrent descriptors bound. So a lot of the quality of life friction points that we hear from developers are getting solved, right? Yes, we acknowledge the Android driver update problem. That's a hard problem to solve. It's not just an IP vendor problem. There's OEMs, and we're working with Google to try and push things along. We do hear the complaints, I promise. Obviously, then we have all the dynamic rendering things. Hooray. This is obviously a huge step forward. And the dynamic rendering local read gives you the fast access to tile memory, the equivalent of things that you had through subpasses in the old functionality. So good stuff. It makes the API a whole load nicer to use. This does come with some caveats. The way that our GPU does state management means this does not drop out trivially for free. There's a bit of state hashing in the driver to match things up. And there were some bugs in the hashing. So there are some small number of states where we have some bugs. This is a good chance to signpost the new errata document we finally published. So GPU vendors are a little bit cagey of having public errata for GPUs. But it was obviously becoming a sticking point, especially with Android, with the long tail of old drivers. So we have now started doing a non-confidential public errata notice, and it's now public. We did an update to it, version 2, just before Vulkanized. So if you've seen it before, go grab the latest one, and there's some more dynamic state bugs in there. So we'll keep that going. As developers hit issues, we'll keep it up to date. It's not every bug. It's not every errata we have, but it's the useful set that app developers are going to run into. Finally, then, just a very quick run through some new tech. So last year's GPUs, the Immortalis G720 series. The big new thing for us here is deferred vertex shading. That bandwidth of going from the full geometry pass to a fragment pass was becoming problematic as geometry complexity goes up, and obviously bandwidth is really, really important. So this has been a very long time coming, but we shipped it. Hooray. So our initial phase now is just doing binning, so it computes position, it does some stuff. Please tightly pack all of your position data with nothing else interleave with it, otherwise we're going to pollute the cache with stuff we're never going to use. We only write back positions and metadata for things, position not always written, and then we defer the full vertex shading until the fragment shading time. So tile by tile, we're going to go and run the vertex shader to compute the data we need. This does come with one caveat of it's quite easy to be vertex bound if you stick things like ray tracing in your vertex shaders, because that's going to get repeated tile for tile. So please be a little bit sensible of what you stick in your vertex shaders. From a terminology point of view, we've now introduced this kind of binning phase and main phase terminology as the two halves of the render pass, just because the old geometry phase and fragment phase naming didn't quite work. So if you use our tools, just be aware the naming has shifted a little bit. But the concept's still there. Hopefully binning phase is smaller, but the main phase is bigger because it's doing more work. But the concept's the same. We're still trying to overlap render passes to get the phases running in parallel. What does this mean in terms of the streams we saw earlier? So first point of note, we've added a transfer stream that's separate from the compute stream. So that removes some false dependencies between compute and transfer. And that's a driver change, not a hardware change. If we can get newer drivers onto older devices, that would also solve the problem there, but currently just newer GPUs. Vertex shading is now running in the main phase endpoint. This means that we're going to release vertex dependencies later. So be a little bit careful if you have quite tight vertex buffer reuse inside a frame. We're now not going to release that dependency until the end of fragment shading. And that may take, therefore, may cause bubbles if you've got very aggressive, narrow temporal scope reuse. So space out your vertex array data reuse across a couple of frames, and that problem should go away. The big new technology in this year's GPUs is the Fragment prepass hidden surface removal. So we've had hidden surface removal for a while, since Mali T620, way back in like 2012, 2013. But it's been getting less effective over time. It's a very simplistic scheme. It's great for hardware efficiency, but it needed to know was something an occluder at draw time. It couldn't cope with shader-based occlusion and alpha testing, for example. So a popular game, making very, very heavy use of alpha-tested foliage. So all of those red fragments are things that are opaque, but because they need alpha testing, our old scheme couldn't use any of that as a hidden section removal occlusion hint, as an example. So in Immortalis G95, so this is shipping in devices you can go and buy now. We added a new hidden subfish removal scheme. And the basic idea is very, very similar to the classical software depth prepass, right? So console rendering for a long time has had the idea of having a software depth prepass. You render all of your opaques depth only. You render all your opaques again, color if depth equal. You then do transparency over the top. Awesome. Pixel perfect occlusion. Everyone's very happy. Okay. You need to render all of your opaque geometry twice. That's not so great for a tiler because we have twice as many things to go and bin and round trip via memory, and bandwidth is evil. So let's do it in hardware, right? We have the binning information, we know the opacity information, we have a depth prepass in hardware. Each tile, so tile by tile, we now have a prepass that runs. It will go through the primitive stream in primitive order, process compatible opaques, skip compatible transparents, and if you've got a complex thing, then it'll just terminate the prepass, fall back to the old scheme, and render as normal. And then the main pass runs for the visible stuff, and you're going to build up your main output. The big goal for developers here is please order your draw call so that you don't break the prepass. If your first draw call in your tile is something which is complicated and therefore kills the prepass, you're going to get no hidden surface removal from this scheme. The old one's still there. But if you can order your draw call so that all of your compatible ones happen first, then your incompatibles, then your transparents, you get as much benefit out of this as you can. So what makes a bad draw call? Non-opaque and right ZS. Right? That's not going to work. We only have one ZS buffer to track around. Non-opaque, the obvious one is alpha translucency. So you're doing some kind of blending. We only have a single state tracker for the whole frame buffer. We don't have one per attachment. It costs too much hardware area. So if you write to a subset of attachments compared to earlier draw calls, that's effectively a punch through alpha for the attachments you're not writing. That counts as transparent, even if the draw call itself is totally opaque. So order your draw call so that you're writing to a superset of attachments that have been written earlier. That's the one that catches most content out, is this kind of sparse draw mask on G buffers. We can't cope with read, modify, write side effects. You have to replay the prepass, and that will have issues. Read-only side effects and write-only side effects are absolutely fine. It's only read, modify, write that has a problem. So things like atomics, where you're using the result. If you modify coverage, write ZS, and use force LEZ as a layout qualifier in the shader, we can't cope with that one. We kind of recover coverage based on the visibility data rather than ZS testing for the main pass. So anything that's relying on the sample coverage, we can't recover the sample mask reliably later. So we're not guaranteed to preserve draw order behavior. So that currently early outs. So if you're using sample mask or helper invocation in the shader and central interpolation for multisampling, if you use helper frame buffer values across warp, this most commonly happens for things like frame buffer fetch, which is specified to actually fetch values from neighboring things. So different derivatives work correctly for decals and things. That can cause a problem as well. So general goal, put all of your good draw calls first, then your bad draw calls, and then your transparents. Kind of guarantees you don't kill the HSR too early. This is done tile by tile, so it's not done for the whole image. So if you've got one or two tiles that you kind of fail out early, it's not going to break the whole frame. So in summary, so high performance mobile is increasingly about bandwidth efficiency. This is a trend that's been going on for years, but it's really getting noticeable. Most mobile GPUs are tile-based. The high order bit is make good use of your render passes, load op, store op, and resolve attachments. Beyond that, the main API impact is scheduling differences. The good news is in terms of best practices, tile-based best practice tends to be a kind of superset of IMR best practice, mostly. So if you do code that is good on a tiler, it's probably going to run fine everywhere else, right? Which is a slightly more conservative implementation in terms of scheduling. And I guess two big new updates to ARM GPUs in the last 2 years. They're transparent to the developer for the most part. They're just going to do their thing. But if you know what you're doing, you can make sure your content's playing along nicely. Thank you very much.
Any questions? Yes, at the back.
You talk about synchronization. Is there any performance difference on Mali between subpass dependencies and pipeline barriers?
Not really, no. I guess like things like SEMs have got a CPU implication because you can wait on a SEM on the CPU. So there's a bit more CPU overhead for SEMs because you've got to get the data back to the CPU somehow. So pure pipeline barriers are purely GPU command stream side. So in terms of GPU performance, no difference. A bit of CPU overhead for things that the CPU can do.
Hi. So earlier in your slides, you showed a comparison with a console of unspecified architecture. Were you comparing an ARM architecture with the mobile processor?
No, so this is purely like if you go and look at public material on like last gen consoles and previous gen consoles around GPU performance, so GPU bandwidth, GPU FMAs, you end up with these kind of numbers, right?
Okay.
This isn't looking at CPU at all.
Okay. Oh, right. So, all right. So I was trying to figure out the console based on the architecture.
I'm not going to say find me afterwards.
Okay. Thank you.
Just going back to your comment about breaking up large submits, can you give a little more background about how that helps? Like I don't see, other than the fact that it's a separate API call, I don't see how that is causing blocking.
It's purely the latency of the application user doing something to the queue present landing and the thing getting released for the display subsystem. So the latency of user does something on a screen to actually seeing that image can be higher, even though your throughput is still 60 FPS. You end up with slightly higher latency.
Because one of those submits this. No.
So
I see. Yes. Okay. You're just saying you're holding back.
Yes. Exactly.
Rendering anything until you've got everything.
Yes.
Okay. And I understand that. I thought you were indicating that there was some kind of blockage between render passes.
Purely just the GPU's idle, waiting for work, and you're not giving it work to do.
Any other questions? In which case, let's thank our speaker.